All right, hello. So in this video, I'm going to compare two different types of problems, one coming from normal random variables and another one coming from coin flips. And we're going to see how they're the same and how they're different and what changes going from sort of continuous type stuff to discrete type stuff. And that's eventually going to lead us to this thing that I actually want to get to, which is linear regression versus logistic regression. And you're going to see that they're very similar, but just kind of for two different problems. So they're kind of like two mirror universes here, and I'm going to try to keep everything in these two columns on this table to show you what's going on. So one column is for normal random variables, and the other column is for coin flips. So normal and coin flips, I think these are their like street names or like they're like colloquial names. They also have fancy names, which are named after dead mathematicians. So what are their fancy names? It's a Gaussian versus a Bernoulli. And to visualize what's going on, I have everybody's favorite tool, Desmos. So let's open up Desmos. And in Desmos, I have plotted a Gaussian, which is this green bell curve. And you can see that it's a bell curve, and you can change what the mean is. So I have a little slider here, M. M stands for mean, that you can slide around, and you can change the mean of this Gaussian random variable. Ooh, actually, let's even animate it. So by changing the parameter M, we can change the mean of this Gaussian random variable. Okay, it went all the way to minus 10. So it's a continuous random variable. It's very likely to be close to the mean. This bell curve represents the probability density of the thing. On the other hand, for a Bernoulli random variable, we have a parameter p that we can change, but we have a little bar graph instead. And that's because the Bernoulli random variable, or the coin flip random variable, it can only be either 0 or 1. So if we zoom in a little bit, we should see that it's either 0 or 1. And the probability that it's either 0 or 1 is some number between 0 and 1. And of course, they have to add up to 1. So there's some parameter p that we can use to change this probability. And so that's really fundamentally a huge difference between these. One of them is continuous and can take on any value, and it has probability densities. And the other one is discrete. It's either 0 or 1, and it can only take on two values, 0 or 1. So let's write that into our table. So let's say, what are they? So for Gaussian, it has a probability density. So probability density, I'm going to write with rho. So you don't want to write the probability, like this is tempting, the probability that the Gaussian equals x, right? But the probability that the Gaussian is any real value is 0 because it has probability densities. So I'm going to write probability density. I'm going to use rho for density. And I'm going to say G for Gaussian. The probability density that it's equal to some value x, it's this bell curve formula, 1 over square root of 2 pi e to the power 1/2 x minus mu squared, where mu is the mean. So maybe let's add a column as well, or a row, for what are the parameters. And we have, for this one, we have mu, which means the mean. That's what it stands for. Of course, you could also do it with sigma, changing the variance, but I'm not going to do that. So, and the notation people use for this random variable is Gaussian mean mu, and I'm putting variance equal to 1 here. So that's a Gaussian. On the other hand, coin flips, what are coin flips? These really do have probabilities. So these really do have probabilities. The probability that the coin flip, I'm going to do B for Bernoulli. The probability that the Bernoulli random variable equals some value y. Yeah, let's use y's instead of x's everywhere, because I want x's for something else later on. So let's do y's everywhere. The probability that you're equal to some value y, it's just p, or 1 minus p. So I'm going to do it like this, and I'll say it's the probability is p if y equals 0, and it's 1 minus p if y equals 1. If y equals 1. So it's either p or 1 minus p, and we have this parameter p, which is probability, the probability of 0. And this is always between 0 and 1. On the other hand, the mean for the Gaussian can be any real number. So this is in some real value thing. So those are the setup of the two variables. And now we're going to see what is it like to look at data that's generated according to either the Gaussian or the Bernoulli, and what is it like to classify them? And that's eventually going to lead us to this linear regression versus logistic regression problem. Okay, maybe I shouldn't use the word classify. I should use the word regression. We're trying to estimate using the data. So what would data from these two variables look like? So I have another Desmos for that. So in green, we have like things that are Gaussian-y, and in blue, we have things that are Bernoulli-y. And so the Bernoulli one is always 0, 1 valued. So if you look at the table, it's either 0 or 1. In general, if you have two classes, it's a good fit for this kind of thing. The Gaussian is kind of spread out like this, and it can take on any possible y value. And here's the thing I want you to make sure is clear in your head, is on the x-axis is covariates. They're things that give you information about the y value, and that is affecting the parameters p and mu. So when you're given data like this, really your job is let's pretend that for every fixed value of x, so we're going to fix a value for x. So we say like x equals 5, and we'll draw that as a dotted line. Let's draw it in orange and dotted. So for every fixed value of x, you should think about data being generated at x equals 5. For the blue data set, it's a Bernoulli with some parameter p that depends on this x equals 5. And for the Gaussian, it's some parameter mu that depends on x equals 5. And we're trying to estimate what is that value of mu and what is that value of p. So going back to our table, just to be crystal clear, we're going to add a row. Let's add a few rows. What is the estimation task? So given samples, so x, let's call that x1, g1, g for Gaussian, all the way up to xn, gn. So those are dots, right? I'm drawing the value of the random variable on the y-axis. On the x-axis, I have these covariates, x. And what we're trying to do is estimate the value mu, and it can depend on x, right? So the value of mu changes as you change the x value, just as you saw in here. And our job is to estimate for every single x value, estimate what is the mu value for the green. And similarly for the Bernoulli, you have to estimate the p value. Okay, so given samples x1, b1, all the way up to xn, bn, estimate the value p of x. Okay, and again, I'm using b for Bernoulli, g for Gaussian. I'm doing all the Bernoullis in blue and all the Gaussians in green. I will do one other thing. For estimated values, I'll put a hat. So I'll say we're going to estimate p hat, and over here we're going to estimate mu hat. Okay, how are we going to estimate these things? What is the objective function we're going to use to estimate these? So we need an objective function. So this is the thing, like this is how we measure how good our estimate is compared to the real thing. And I can tell you already what it is for the normal random variables. It's everyone's favorite mean squared error, the MSE, which is the mean squared error. And what is the mean squared error? It is, I do this GI minus hat mu squared, and I add this up over all our samples. Sum from I equals 1 to n, and this we're going to call this the MSE. So this is how we would measure how good we're doing. We try to minimize this. So whatever we do to estimate mu hat, we calculate this on our sample, and we would like it to be small. That means that our mu hat of xi is very close to gi, hopefully. Okay, what is it for the Bernoullis? What is it for the Bernoullis? And we're going to find out in a minute. But I want to show us not to just take it for granted, but I'm going to show you how. We come up with this mean squared thing. Where did that actually come from, and what is it doing? So, and that goes through using the likelihood. So the objective function for the Gaussian, this mean squared error, is actually related to this distribution. And these sum of squares is related to the sum of squares here. Oh, by the way, look, I'm missing a minus sign. That's good to know. So it has something to do with something called the likelihood. The likelihood. So what is the likelihood for the Gaussian? I'm going to use this symbol, fancy L for likelihood. And the likelihood, it's a little bit like a probability, but in reverse. So in a probability, actually, let's write that out first. Let's write out the probability first. So the probability of data. So I'm assuming that all of these data points are generated sort of independently. So what is the probability of data that is generated? So this is the probability for one single point. So what is the probability of getting all of these points? So the probability, and again, it's probability density, to see the data that I see. So the probability that we see the data that we see, given what the actual mean is, given the real function mu of x. What is that? Well, they're independent, so you just do the product of the probabilities for each independent point. So it's the product from I equals 1 to n, and I would do yi minus mu of xi. Okay, so how do I make this a little bit nicer? Let's do a display style here, and put this in here. Make it look, and just barely fit. So if you were given the real function mu, and you really knew what mu was, the probability that you see the data is given by just the density for the Gaussians. The likelihood is the same kind of idea, and it's the same formula, but it's in reverse. So it's saying, given the data that we have, what is the likelihood of seeing a particular mu value? And so the likelihood for some estimate, mu of x, given the data that we have, so again, given all this data, is this stuff in reverse. And I need to be in the math mode, okay. Given all this stuff, it's the same formula, but now, see, it's no longer a probability because now we're thinking about it as a function of the mu hat. Okay, and I lost my likelihood. All right. So it's the same function, but it's really important to keep track of the difference here. So this one really is a probability density. Like if you integrated it over all possible x's and g's, you should get 1. Whereas this one is a likelihood. It's telling you something about the estimate mu hat, how likely it is given the data. That's what it represents. Okay, and I've realized I've been using y here, but it should say g for Gaussian, so we don't get it mixed up with the Bernoullis. Okay, what on earth does this have to do with the mean squared error? What does it have to do with it? Is there anything to do with it? Well, one way you can always make an objective function is to maximize how likely something is, right? That would be a reasonable way to try to estimate the parameter mu. So you could maximize this likelihood. And in fact, because the likelihood is a product, it's a little bit easier to maximize the log likelihood. So what is the log likelihood? It's the log of this guy. And what is this guy? Actually, let me see here if I can make this table just a little bit wider so our formula fits in a little bit better. Let's make it just a hair wider. Okay, there. Very nice. So the log likelihood is the log of the likelihood of hat mu of x given, I'll say, the data, just to not repeat everything too much. And it turns a product into a sum. So now we have the sum. And what do we have? Okay, we have these 1 over square root of 2 pi. Those are going to be some constant, right? So this 1 over square root of 2 pi, technically it's part of the probability distribution. In terms of maximizing or minimizing the likelihood, it has no role. So I'm just going to put plus a constant, plus c, where the plus c represents all of this nastiness from the 1 over square root of 2 pi. What does matter is the stuff in here. And so inside here, I'm going to have a minus a half taking the log. I'm going to actually, let's make sure we're clear that this is the natural log. So people say log likelihood, they mean the natural log. Natural log. And when we take the natural log, it exactly cancels out this e. So we get minus a half, and then we have gi minus hat mu of xi all squared. Okay, plus c. So the log likelihood is a minus 1/2 times all this stuff. Let's just simplify it a little bit. because it's minus a half, then I have the sum from I equals 1 to n, gi minus hat mu of xi all squared plus some constant c. And you can see that's extremely closely related to the mean squared error. And in fact, this is where the mean squared error comes from. It comes from, let me add a row here. The mean squared error is actually negative the log likelihood, is negative the log likelihood. So when you're minimizing the mean squared error, what you're actually doing is you're maximizing the log likelihood. You're trying to make you're trying to choose parameters to make the data you saw as likely as possible. Now that we know this, now we know this connection between mean squared error and negative log likelihood, now we can do the same thing with the Bernoullis. And we can figure out what would be the type of error function, what are these question marks, that correspond to Bernoulli data. So that's what we got to do. So we're just going to repeat all the steps using this Bernoulli formula rather than using the Gaussian formula. The first thing I'm going to do a quick little simplification. Of course, this is an absolutely correct formula. It's probability p if y equals 0 and 1 minus p if y equals 1. But I'm going to just add one thing here quickly, which is I'm going to write this in a funny way. I'm going to write it as p to the power y times 1 minus p to the power 1 minus y. Okay, and should I try to fix this? Let's try to fix this. So what do I want to do? I'm just going to fix this formula real quick. Okay, so the probability that the Bernoulli equals some value y is this, and this formula can be written as p to the power y times 1 minus p to the power 1 minus y. So this is a bit of a kind of a hack. So if y equals 1, you're supposed to get p, and then if y equals 0, you get the other one. Oh, I guess do I have it backwards? Let me just double check my notes here. Maybe I have everything backwards. Okay, I think I really want it to be the other way around. I want it to be the probability p, I want that to be the probability that you're equal to 1, and I want 1 minus b to be the probability you're equal to 0. And that way, the probability, if it's the probability of being 1, a nice thing happens, which is also, let's write it over here, also, p is also the average value. So it's the expected value of b. Right? Because if it's either 1 or 0, then the average value is just the probability of being 1. That's still p. So that makes things a little bit nicer. So it's p to the y times 1 minus p to the 1 minus y. So if I have a bunch of data, x1, b1, all the way up to xn, bn, what is the probability of my data? The probability of my data, given the true value p, given the true value. So now we have this true function p, which tells you the actual probability given some value x. What is the probability that the Bernoulli is either 1 or 0? Well, it's a product. So it's the product I equals 1 to n. And it is simply this formula. So this is why this formula is nice. It's a lot easier to multiply out than the other formula. So what is the actual formula here? P of xi to the power bi, and then I have a 1 minus p of xi to the power 1 minus bi. Okay, and again, same problem as before, slightly running out of room, but let's just copy this and we'll add a line. Okay, so there's our probability formula. Before it was a probability density. Now it really is a probability. So that's nice, easy to interpret. And just like before, so we don't know what our objective function is going to be. We're going to discover that. But I'm going to get to it by doing the likelihood. So the likelihood of some guess for the probability function p, given the data that I have. So given x1, b1, so n observations of these Bernoullis. What is that? Again, it's the exact same formula as this, but the interpretation is different, right? So we're thinking of it as the data is fixed, and we are imagining how is p hat depending on things. So here it should depend on p hat. So hat p and hat p. Okay, and once again, kind of a nasty looking thing, but it's a product. So if you take the log, it should get simplified. So we do the log likelihood, and what do we get? We get the log of the likelihood hat p of x given, just say the data again. And what is that? Again, it's a sum over the data. And this time, we have to do the logs a little more carefully. So the product does become a sum. When you do the log of the product of two things, it's the sum of those two things. So there's going to be the log of p hat to the power b times 1 minus p hat to the power 1 minus b. And when you have a log of a power, the power hops down and just multiplies in front. So you're going to have bi, a log of hat p of xi plus 1 minus bi. Then you're going to have the log of your estimate xi. Okay, and I made one mistake. It should be a log of a 1 minus p. And okay, again, it's not fitting. So let's copy this all over. Yeah. Okay, let me wrestle with my computer for a second here. Okay, so I fixed it. So the log likelihood is the sum over the data. Bi, that's the value, either 1 or 0, right? So going back to our Desmos, it's either 1 or 0. Each observation is 1 or 0. And then we multiply that by the log of p hat plus 1 minus bi times the log of 1 minus p hat. That's the log likelihood. And so a valid thing to do is to take the negative log likelihood. The negative log likelihood. So this would be the thing that you minimize over here. And this has a name. It is, again, some people call it a loss function. It's called the cross entropy loss. And it's the negative log likelihood of the Bernoullis, just like the mean squared error is the negative log likelihood of the Gaussians. And so what is the formula? It's exactly this formula with a negative sign in front of it. So let's call it the cross entropy loss, CE loss. And it's exactly this formula over here. So to see what this looks like, in a very simple situation, let's completely ignore the x's and just look as a function of p, right? So pretend p hat is just one number that you're trying to estimate, and you're given, some b's and g's. What does this function look like? And I think the easiest way to visualize this, to make things a little bit simpler, is to get rid of the data. Okay, how could you possibly get rid of the data? The whole point is to try to do everything as a function of the data. Well, the data is drawn from this distribution, right? Like, we're assuming the data is drawn either with mean mu or with mean p. So we can ask for what happens on average. So let me add this, actually. We can add this. The objective function, right? So given some actual data, this is what we're actually trying to do. But really what's going on, the objective function is approximating something about the true distribution mu. And if we could figure out a way to write this, connect this thing, which depends only on the g's and the x's, to something that depends on the mean mu, then we can, understand it only in terms of the mean mu and not have to worry about the data. And really what I just want to do here is I want to say the objective function, this depends on the data. The data is random, so we can talk about the average of the objective function. So this is the average of the objective function over the data. So this is like the average mean squared error that you sort of expect to see. And okay, just to make things a little bit cleaner, I'm going to add a 1 over n to the mean squared error. Okay, indeed, if I'm going to call it the mean squared error, I better have a 1 over n, right? Otherwise, it doesn't make any sense. So 1 over n. And if you take the average, you have the average of g, which is supposed to be Gaussian with mean mu, minus mu hat squared, So this is the average. So it's the average of G minus hat mu of X. And what we're given is that G is distributed like a normal with mean, the real mu, and variance 1. Okay. So that's really what's going on. Often people put this information, they put it as a little subscript over here. But that's really what's going on. So what do we end up with? So this is, I guess, conditionally on X. Well, let's say the mean squared error conditionally given the value of X. And so again, this is this idea of taking a slice only at one value of X. Then you get this thing. And what is this? This should be a squared. All right. So what is this? This is like a calculation you can do anytime you're squaring a Gaussian. It's going to involve the variance of the Gaussian and also the mean. And in fact, in this case, you can check. This is the variance bias decomposition that we did a while ago. You can check that what you get is mu of X minus hat mu of X squared plus the variance. And the variance in this case is 1. So on average, what do you get at some value X? You get the difference between the true mu and what you estimated squared plus the variance. And this is sort of the irreducible part that you can never get rid of. And the 1 is really coming from here. So if I had done sigma squared instead of 1, then it would be sigma squared both here and here. Okay, so that's the average of the objective function over the data. And you can see it only depends on the parameters mu. Sort of the samples we got, the GIs are all gone. And we can do the same thing for the cross entropy loss and see what we get. So we can do the expected value of the cross entropy. And we'll do it again, we'll do it at some fixed value of X. And so what are we gonna get? Let's start it to be all in one line. It's going to be the average of this formula, b log of hat p of X plus 1 minus b of log of 1 minus hat p of X. And again, this is not for any fixed value b, so I'm not writing b1 or b2. I'm thinking of b as being random and chosen according to this Bernoulli thing, with probability, true probability p, where p is some given thing. So this is the difference between p and p hat. P hat is our estimate, and p is the real thing. And if you calculate this, okay, the log of p hat and the log of 1 minus p hat, those are just constants. So you just need to know how to do the average of b. What's the expected value of b? But we know the expected value of b, it's p. That's exactly why we chose p the way we did. So what is this expected value? Well, the expected value of b is p. So here we have p of X. And here we have ln of p hat p of X. And here we have 1 minus p of X. And here we have ln of 1 minus hat p of X. So there's the formula. And again, it doesn't depend on any of the observations. It just depends on the true value p and the estimated value p hat. So to write it simpler, let's add a line where we, just to hide the dependence on the x value, the same thing with no x's. No x's. So what is it over here? It's mu minus hat mu hat. No, I have two hats. Okay, mu squared plus the irreducible part, which is 1 in this case. And over here, it's a very funny looking formula. P ln hat p plus 1 minus p ln of 1 minus hat p. Okay, and let's see what these look like. Okay, I realized I did something silly. I never put the minus sign in. So the cross entropy loss is supposed to be negative all this. So there's negatives everywhere. And you'll see why that is because I'm going to plot it in a second. And you'll see why the negatives are crucial to have. Otherwise, things will look a little bit funny. But let's plot these. These are functions we can plot. So let's go back to Desmos. And we will plot it. So here's Desmos. This was our data, but this is our Gauss versus Bernoulli thing. And I have things set up to plot the loss. So one of them is x minus the mean squared. And, okay, it's plus 1, right, for the irreducible part. And so you can see how this happens as you change the mean value. This just moves around. It's a quadratic formula. The best possible estimate is that x equals mu. So here I'm using x as our estimate, and m is the true value, right? So this is what the distribution looks like. This is what our estimate looks like. Okay, so that's fine. So this 1 is the irreducible part. You just want to get as close to the vertex here as you can. Very simple stuff. This is like what you learn in grade 10. The other one is a lot more complicated. So let's look at what this looks like. So here's the formula. And again, I'm thinking of p as the true value. So this slider p is setting the true value of our probability distribution. So here's the visualization, what the probability distribution looks like. One more time, p tells you the true value. And our estimate for what is the value of p can be anything between 0 and 1. And so we're going to see when I plot this, we're going to get a function between 0 and 1 that's going to tell us how close we are to estimating this p. And again, I'm missing a minus sign. Let's see what happens if you plot it. If you forget the minus sign, what happens? Well, now it's negative. So it lives down here. So to make it positive and make it look like something we want to minimize, I put a negative sign in front everywhere. So negative sign and negative sign. And what does it look like? It looks like a funny curve like this. So it looks, it looks a little bit like a quadratic equation, especially if you're close to a half. Then it looks very quadratic-y, but it always lives between 0 and 1. So you can never escape x equals 0 and x equals 1. Let's color those in. Blue and dotted. And I want it to be blue and dotted over here, please. I think I have to turn it on first. Okay. Blue and dotted. And let's zoom in so that we're only ever between 0 and 1 because these are the only values you would ever guess, right? Okay, and let's leave like a little bit of buffer so we can see what's going on. Okay, there we go, perfect. So when p is close to a half, it's really close to a quadratic, but it kind of explodes at 0 and 1, right? It has like these asymptotes at 0 and 1. But when p is very close to like 1, it kind of starts to look a little funny, and it's kind of asymmetrical. And this is something that's very different between the Bernoulli case and the Gaussian case. In the Gaussian case, if you look at the formula, let's look at the formula. Mu and mu hat are kind of symmetric, right? Mu and mu hat are symmetric. It's just how far apart they are. So if you want to know how good you're doing, all you need to know is the difference between mu and mu hat. In the Bernoulli case, it's different. So p and p hat are very asymmetrical. And this is, for example, this is saying that, if the true value is 99% and you estimate 95%, so you sort of like underestimate by 4%, that's different than overestimating by 4%. Like, it's not symmetric. It doesn't just depend on the difference p and p hat. It sort of depends on how both are combining through this like crazy looking cross entropy formula. So really this is telling you like the likelihood of something with probability p, what is the likelihood of it happening according to p hat? That's really what's going on, and you end up with this crazy looking graph. So I think that's kind of cool. One thing to note in the Gaussian case, right? Just looking at the Gaussian formula again, which I guess I have to bring mu somewhere into the picture. Yeah, in the Gaussian case, the minimum is 1. We know what the minimum is. What is the minimum for this guy? Right? It looks like it also, again, it depends on what p hat is, which is really interesting. It turns out the minimum is exactly when p equals p hat. Like, that's not surprising. That would be the best possible estimate. So if you put in x equals p, you get the minimum of the cross entropy loss. So let's do this with a dotted line. That's the minimum at x equals p. And what is the minimum value? Well, the minimum value is this p log p plus 1 minus p log 1 minus p, all with a negative sign. So this is the minimum value, y equals so much. So that's the minimum value. And this value is called the entropy of the true distribution P. So we can add this as a line to our chart. The minimum of the loss. So here it's 1. Very simple. This is the irreducible variance. And over here, it's this function p ln p minus 1 minus p ln of 1 minus p. This is called the entropy of the distribution. The entropy of the distribution. And this is sort of like an information theoretical, even if you know what p is, you can never estimate better than this. I mean, it's the same thing for the Gaussian. So it's kind of a cool thing about Bernoulli's. Okay, so what have we done so far? We figured out what is the loss function to use. And in part 2 of this sort of video, I'm going to use this loss function to figure out what is the same and what is different between linear regression and logistic regression. And we're going to see why is it the logistic regression, where is the logistic hiding? So far I haven't mentioned the logistic function, the sigmoid function. I've just come up with this thing, but we're going to see that actually the logistic function is very closely related to this cross entropy loss that we discovered. And so the reason people call logistic regression is they're doing the cross entropy loss, and they're doing it in a special way so that things magically simplify and cancel. So I'm going to make a new video for that one where I just do linear regression versus logistic regression and show this little miracle that the cross entropy loss plays really nicely with the logistic function.